Today we're going to work through the major probability distribution concepts used in statistics, and before we calculate anything, I want to anchor us in how to decide which concept applies to which situation. Most mistakes in statistics don't come from arithmetic. They come from choosing the wrong tool. So as we go, I want you to listen for the type of question being asked, because that tells you which distribution fits. A helpful way to think about this is to ask what kind of quantity you're working with. If you are counting things, you are in the discrete world. If something repeats as a yes or no outcome over a fixed number of trials, you are in binomial. If you are measuring something like scores, heights, or times, you are in normal. And if you are working with averages from samples, you are using ideas from the Central Limit Theorem. That decision comes before any calculation. We're also going to anchor everything in StatCrunch, since that is the tool many people use to compute probabilities. StatCrunch is doing the same mathematics that statisticians have always done. It is calculating probabilities by finding areas under curves or combining known probabilities. What matters is that you give it the correct information, and then interpret what it gives back. Let's start with discrete probability distributions. Discrete probability distributions exist because sometimes outcomes are countable and separate, and we already know how often different outcomes occur. These are not measurements like time or height. These are counts. When we use a discrete probability distribution, we are organizing known probabilities so we can answer questions about likelihood. Think about situations like the number of customers who arrive in an hour, the number of emails you receive during a shift, the number of defective items in a batch, or the number of questions a student misses on a quiz. In all of these cases, the outcome can only be a whole number, and you can list all possible outcomes. Now imagine a short quiz where the number of questions missed can be 0, 1, 2, or 3. Based on past data, the probability of missing 0 questions is 40%, missing 1 question is 35%, missing 2 questions is 20%, and missing 3 questions is 5%. This fits a discrete probability distribution because the outcomes are countable and each one has an assigned probability. Before answering any question, it's important to check that the information makes sense. When you add all of the probabilities together, they should total 100%. Once that checks out, we can answer questions like how likely it is that a student misses at most 1 question. At most 1 means 0 or 1, so we combine those probabilities from earlier of 40% for 0 and 35% for 1. Then we see that the result is 75%. That tells us that missing 1 or fewer questions happens most of the time, which matches what the data suggest. Now let's move to the binomial distribution. The binomial distribution exists for situations where the same process repeats a fixed number of times, and each time the outcome is either success or failure. It answers questions about how many successes we should expect when something repeats. Binomial situations have a very specific structure. There is a fixed number of trials. Each trial has only 2 possible outcomes. The probability of success stays the same each time, and each trial is independent of the others. Examples of binomial situations include the number of heads in 10 coin flips, the number of students who pass an exam out of a class when the pass rate is known, the number of defective items in a sample when the defect rate is known, or the number of free throws made out of 5 attempts. Now imagine a free throw shooter who makes a shot 70% of the time and takes 5 free throws. We want to know the probability that the shooter makes exactly 3 shots. This fits the binomial model because the number of shots is fixed, each shot is make or miss, the probability stays the same, and the shots are independent. In StatCrunch, you would go to the binomial calculator, enter 5 trials, a probability of success of 0.7, and specify exactly 3 successes. StatCrunch gives a probability of about 31%. That tells us that making exactly 3 out of 5 shots is a fairly common outcome for a shooter, with a 70% success rate. Now let's talk about the normal distribution. The normal distribution exists because many real-world measurements cluster around an average, with fewer values appearing farther away from that average. This pattern shows up naturally in things like test scores, heights, reaction times, and measurement error. Normal distributions are used when the variable is continuous, not countable. Instead of asking how many, we are asking how much. Normal distributions help us answer questions about what percent of values fall above, below, or between certain cutoffs. Examples include questions like what percent of students scored above a certain score, what percent of products fall within a tolerance range, or what percent of people fall below a certain measurement. Suppose exam scores are normally distributed with an average of 75 and a standard deviation of 10. If we want to know the probability that a randomly selected student scores above 90, we can use the normal calculator in StatCrunch. We enter the mean as 75, the standard deviation as 10, choose greater than, and enter 90. StatCrunch returns a probability of about 6 to 7%. That tells us that scoring above 90 is relatively uncommon, which makes sense since 90 is well above the average. We can also use the normal distribution to find probabilities between two values. Using the same exam score distribution, suppose we want to know the probability that a student scores between 70 and 85. In StatCrunch, we choose between, enter 70 and 85, and use the same mean and standard deviation. The result is about 53%. That tells us that just over half of students score in that range, which makes sense because the range includes the average score. Finally, let's look at the Central Limit Theorem. The Central Limit Theorem exists because averages behave differently than individual values. When we take averages of samples, random variation smooths out. As long as the sample size is large enough, those sample averages follow a normal distribution and have less spread than the original data. Central Limit Theorem questions are always about sample means, not individual observations. You'll often see language like sample average or mean of a sample. Examples include the average wait time of a sample of customers, the average score of a sample of students, or the average weight of a sample of packages. Suppose service times at a restaurant have an average of 12 minutes and a standard deviation of 6 minutes. If we take a sample of 36 customers and want the probability that the sample average is less than 10 minutes, we use the normal calculator in StatCrunch again. This time, the mean stays 12, but the standard deviation becomes the standard error, which is 6 divided by the square root of 36, or 1. When we choose less than and enter 10, StatCrunch gives a probability of about 2 to 3%. That tells us that a sample average that low would be quite rare if the true average really is 12 minutes. As you work through problems like these, keep grounding yourself in the question first. Ask whether you are counting, repeating yes or no outcomes, measuring a continuous variable, or working with averages. That decision tells you which probability distribution concept applies. StatCrunch handles the calculation, and your job is to explain what the probability means in the real situation.